First, I would like to ask whether you have any questions about login, the GPU cluster, or any other questions. Okay. Yeah, there were some questions on login. Okay, but now I presumably they are all solved. Okay. Yeah. So let me start today's lecture. Okay. Yeah, today I'm going to cover the topics on how to solve Laplace and Poisson equation on a two-dimensional lattice with boundary conditions. Okay. Yeah. I think you have solved similar kind of problems. Okay. Yeah. In your courses on electricity and magnetism, as well as the electrodynamics. Okay. But there, for analytic solution, okay, there are some restrictions. Say the boundary condition has to be, quite special, or with some, in general, okay, you cannot solve such boundary problems, especially the boundaries irregular, for example, okay. In any case, okay, no matter what's the boundary and how are the charge distribution inside this boundary, okay, numerically, we can always solve the problem. Okay. So first, let me talk about the field theory on a two-dimensional lattice. Okay. So this field theory is just general field theory. Okay. Any field theory, okay, which has a field variable, okay, in any space-time point. So let's make things simple. Okay. Only consider this two-dimensional space. Okay. And in order to do the numerical computation, I have to first discretize this two-dimensional space into two-dimensional lattice. Okay. Then I can compute the field variables on the lattice side. Okay. Yeah, and then this gives me the solution. Okay. Yeah, and of course I can increase the size of the lattice. Okay, say more points along each direction. Okay, then we can get a more accurate pictures. What's the solution? Okay, look like. Yeah. So, but all my solutions are numerical. Okay, in terms of numbers. Okay. Yeah. So suppose I have this 10 by 10 lattice. Okay. So on this two-dimensional lattice with some boundary condition, and then this lattice is a 10 by 10. Okay. Yeah. And then what are the field variables? Okay. So the field variables is the phi xy. Okay. So this is the coordinate is the x and y. Okay. And phi is the number. Okay. This number can be a real number or complex number. Okay. Depends on what kind of field you are talking. Okay. Yeah. If this field is the classical electrostatic potential, then it's a real number. Okay. But if you're considering the quantum field theory, okay, or any other field theory in general, okay, this field variable can be a complex number. Okay. And at each site, okay, it can have just more than just one of this field variable. Okay, this field variable can be a sequence of an ensemble of numbers. Okay, so that means it has the internal degree of freedom. Okay, yeah. For example, the electromagnetic field. Okay, you have the electric field and magnetic field. You have the EX, EY, and EC, and then the BX, BY, and BC. Okay, so in the three-dimensional space, okay, and time also included. Okay, space-time. Okay, then you have the EX, EY, EC, and BX, BY, BC. Okay, and they are all variables of the x, y, z, and t. Okay, so so now in this case, okay, only on the two-dimensional lattice. So it only depends on this x and y coordinates. Okay? And to make things simple, okay, say phi is say for example the electrostatic field, then phi is just a real number. Okay. Okay. Now the lattice, okay, suppose there's n x size in the x direction and the ny size in the y direction. Okay. So the psi number x is from 0 to nx minus 1, and the psi number in the y direction is from 0 to ny minus 1. Okay, and the total number of size is nx times ny. Okay. Usually, okay, I can use just one index to represent x and y. Okay, I don't need two coordinate. Okay, I just use the one number index I. Okay, so this is called a psi index. Okay, so if I compute the psi index according to this, okay, x plus nx times 1. Okay, then the I is going from 0 to nx times ny minus 1. So it goes through every size. Okay, but then that means for fixed y at y equals 0, I go through all the x. And then at y equals 1, I go through all the x, okay, and so on, okay, yeah. So with this one index, I set the psi index, then I can put the few variables labeled, put them on just one column, okay, and then this just like a vector, okay. So from phi 0 to phi n minus 1. And then this is called a field vector, okay? So to know the solution of this vector, okay, and this is the all the field, okay, in this on this two-dimensional lattice, okay? So this is the goal, okay? Yeah, given the boundary condition and what are the field, okay, on each side, okay? So. Any questions so far? No. So I said, yeah, it was a general description. Now let me consider the special case, say the classical field theory of the electrostatic potentials. Okay. So the field variable at the site, okay, xy is the real number. Okay, so the field variable at every site is a field number. Okay, is a real number. Okay, yeah. And x what goes from 0 to nx minus 1, y from 0 to ny minus 1. Okay, yeah. So for the electrostatic potential, then I have to solve the electrostatic field Laplace equation. So there's the Laplacian phi equal to rho, okay, and that's the Poisson equation, okay. If rho equal to 0, and that's the called Laplace equation. But in general, that's called with the charge density rho, okay, then this is called Poisson equation. Okay, yeah. So first, I have to write the Laplacian, okay, in discrete form. Okay, so the Laplacian in the continuum is a second derivatives, partial derivatives in x and partial derivatives in y, second derivatives. Okay, yeah. So this second derivatives of phi in x, okay, can be written as a discrete form. Okay, so this is the x plus a holding y is constant. So this is the partial derivatives in x direction. Okay, so second partial derivatives, x plus a, and then x minus a minus 2. Okay, without changing the x, okay, at center, okay. So if you do the Taylor expansion, okay, then up to the order a square, okay, then since there's an a square downstairs, okay, then you can see the a square canceled, okay, and then you get the second derivatives, okay. So that means in the limit when a go to 0, okay, this finite difference, okay, is equal to the second partial derivatives of phi with respect to x. Okay. Similarly, okay, I can write the second partial derivatives of phi with respect to y, okay, in this discrete form. Okay. So now adding these two terms together, okay, then I have the x plus a, x minus a, y plus a, y minus a. Okay. So these fields are the labels of the x and y. Okay. Because x in 2 dimensions, okay, x, y, any side has four labels, okay, in x direction, positive, minus, in y direction, positive, minus direction. So there are 4 labels, okay. And if in the 3-dimensional, then each side has 6 labels, okay. Yeah. So this Laplacian phi, okay, put in this discrete form, okay, this amounts to matrix, okay, multiply the phi. Phi is the phi vector, okay? So phi is this, okay? You can see here, this is the phi vector, okay? And this operation, okay, this Laplacian operator, okay, and on the lattice in the discrete form, okay, yeah, can be written as a matrix D, okay? Yeah, it's easy to write down the matrix, okay? Yeah, since every x and y, there are only 5 non-zero elements, okay? So you can easily fill in the non-zero elements of this matrix D, okay? Each row has 5 elements non-zero. All other elements are 0, okay? So, such a matrix, okay, yeah, is called sparse matrix, okay, because when the lattice becomes very large, okay, then the matrix is n by n matrix. N is the total number of sides, okay? N is nx times ny, okay? Yeah, and in 2-dimensional lattice, on the 4-dimensional lattice or 3-dimensional lattice, okay, then the number of sides is nx times ny times nz, okay? So we can generalize to any dimensions, okay? But on 2-dimensional lattice, the number of non-zero elements on each row or with respect to each side is only 5, okay? There's 1 diagonal elements, and then there are 4 off-diagonal elements, okay? On a 4-dimensional lattice, you can write a 3-dimensional lattice, okay, plus the second partial derivatives of phi with respect to z, okay? Then it becomes, you can add another term, okay, similar to this, except this in the z plus a and z minus a, okay? So that means you will end up with 6 non-zero elements because the label of each side, okay, has 6 labels, okay? Yeah. So that means this can be easily generalized to 3-dimension or any dimension you like. Yeah. So now solving the Laplace equation, okay, amounts to solving this matrix equation, okay? Yeah, this is the continuum form, okay? But we want to solve it on a lattice, okay? In order to get the numerical solution, then we have to put on the lattice such that, okay, the number of field variables is finite, okay? And then I can use the numerical computation to solve the problem. Okay. So so this is the you see this is a matrix. D is the matrix. This is the Laplace operator matrix. Okay, corresponding to the Laplace operator. And phi is a vector. Is the column vector. Okay, and rho. Okay, yeah, is the again. Okay, is the vector. Okay, yeah, and depends on the charge density distribution. on each side. Okay. Any questions up to this point? No? Yeah, you have any questions, you can turn on your mic, okay, ask the question, and also turn on your camera so that I can see you. Okay. Okay. Yeah. Now the question is, what's the lattice spacing A? Okay. Yeah. Once you put the on the lattice, okay, then you only know there's how many lattice sites. Okay. You actually do not know what's the lattice spacing. Okay. So that means in terms of lattice unit. Okay. So you can just set the lattice unit to 1. Okay. Yeah. And yeah. Now the question is, how do you take the continuum limit? Okay. Yeah. Yeah. Let's put this question aside first. Okay. Yeah. Later we will come back to address this question. Okay. How to obtain the continuum limit. Okay. Yeah. So if you have a fixed size, okay, of region, okay, and then the continuum limit amounts to, say, put as many size as you can. Okay. Yeah. So if you have the limit a equal to 0, but the L is a fixed, then that means the number of size will be increased. Okay. So in order to take the continuum limit, you have to use more and more sites. Okay. Yeah. So, but first, let's look at this problem with a lattice spacing, just a lattice unit a equal to 1. Okay. Yeah. Okay. So the question, okay, the equation, the Laplacian phi equal to 0, okay, will give me this equation. Okay. Yeah, phi xy. That means if phi satisfies the Laplace equation, then the phi, okay, at any site, okay, would be equal to the average of these labels. Okay. So this is phi x plus 1, x minus 1, y plus 1, and y minus 1. They are the few on the of the labels of xy. Okay. So this is the, say, the left, right, or just leave left or right. Okay, top and bottom. Okay, you can label like this. Okay, yeah. So this is the labels. Okay, of xy in the x and y direction. Okay, in these two directions. Okay, yeah. Okay, let me see if let me check. Okay, see everyone is okay. Yeah. Okay. Yeah. Question. Yeah. Yeah. You can just go ahead to ask the question. Yeah. You can interrupt.
So,
Yeah. Yeah.
Yeah, sorry. Yeah, I have one question. So, in the while you write down the Laplace equation with the a here,
Yeah.
in the second line, somehow you assume the a to be the small number, but somehow
Yeah.
if you require the a to be 1, whether there is any problem with this kind of the equation.
There's no problem with it. Okay. Yeah. Yeah. You see, usually, okay, when your lattice, okay, yeah, you see that depends on the scale of this problem. Okay. Yeah. Um, for this moment, at this moment, okay. Yeah. I just take the a to 1. Okay. Yeah. But as I said, okay, can we take a smaller? Okay. Yeah. But you cannot just put the, say, 1/2. Okay, because you always have the, yeah. So that means yeah, if you have the lattice spacing 1/2, that means you have a more size. Okay, you with a fixed L. Okay, so we have a more size. Okay, yeah. So in order to give the continuum limit or the or in the limit equal to 0, okay, then you have to get a bigger and bigger of a lattice, okay, with a more and more size, okay, yeah. But then you have to rescale the L, okay, such that, okay, the L is the same for all different number of size, okay, yeah. So this is the how we can get the continuum limit, yeah.
Okay, so after you solve everything, then you will scale the field again. You mean?
Yeah, I have to
Okay.
scale the field again, yeah.
Oh, okay, I see. Thank you.
Yeah, because for the computer, okay, it does not see the lattice spacing, okay, yeah. Okay, let me. Okay, solving the Laplace equation amounts to find the phi, okay, satisfy this equation, okay. So this equation is the Laplacian phi equal to 0, or for if there's a in this region, okay, there's no charge without any charges, okay. If there's a charges, then I have to modify it, okay, easily, okay. I will show you later how to do it, okay. But first, let me solve this problem with the, say, some boundary conditions, okay. Now, let me consider lattice 10 by 10 lattice, okay. And then with the boundary condition, okay, yeah, phi is 1, okay, on the top, okay. So that is the, if I say this is the x, y is 0 here, then here is y is 9, okay, yeah, and then x equal 0 here, and then x equal to 9 on this boundary, okay. So this is a 10 by 10 lattice, okay. So that means the boundary, okay, the phi is 0 on the boundary, except the field on the top here is 1, okay. So this is a very simple boundary condition, okay. Yeah. In general, okay, the boundary condition could be as complicated as you like, okay. Yeah, there may be a temperature gradient along this boundary, okay. And then there's another different variation along this, okay. So this does not cause any problem. You just specify what is the boundary, okay. Say, for example, the temperature here may be particularly high, okay, maybe 10, okay, 1, okay. And then the rest are 0, okay, it's okay, okay. So you can imagine, okay, any boundary condition you like, okay, you can impose it, okay. Yeah. And then this, with such a boundary condition, that means the temperature on the boundary always satisfy this specified condition, okay? This boundary condition, okay, fixed at all time, okay? So with a given boundary condition, okay, now the question is, what are the few variables, okay? In this case, the electrostatic potential, okay? Inside this region, okay? So let's go ahead to solve the Laplace equation, okay? Discretize the Laplace equation on this lattice, okay? So how can I find the phi, okay, satisfy this discrete Laplace equation, okay? So I just start from any phi, okay, any initial phi. And then I do an iteration, okay, iteration. And after each iteration, the phi are updated, okay? And then eventually, okay, the phi, okay, we will approach the values, okay, such this equation is satisfied, okay, the Laplace equation is satisfied. And the difference between this and this will be as small as you like, up to the precision of the numerical I mean the numbers in the computer. Okay, so that's say the stopping criteria. Okay, you set the stopping criteria. Say what kind of accuracy you want, and then you stop at that point, and then that's the answer you want. Okay. Okay. Now let me go to the exactly how do we do the iteration. So with any initial boundary, initial configuration. So given the field initially, okay, any as arbitrary as you like, okay, random, okay, is fine, okay, yeah, satisfy the boundary condition to with any initial configuration, okay, and satisfy the boundary condition. That means the boundary condition is fixed, okay, but then the inside, okay, could be anything you like, okay. You can set them to be 0, fine, okay. You can set them all to be 1, is fine. You can set all the field to be random values, okay, it's fine, okay. Doesn't matter what kind of initial configuration. Eventually, you get the configuration of the field values to satisfy the Laplace equation, okay. That's the point, okay. So I would do the iteration, okay, according to this recursion relation. So I equals 0. So this is the given. Okay, this okay. Initially we know what was the phi at every point, and then I update it according to this algorithm, this recursion relation. Say I is the iteration. So I equals 0 is initial configuration. I equal 1, okay, is equal to this phi 0 of the. So that means that if I add the labels, okay, add the labels of each side, okay, and then replace this phi by this new phi, okay, and that's updating, okay, update the field variable on this side, okay, yeah. So and then I go through every side, okay. So I go to each side and then add the labels, these 4 labels, okay. Add these 4 labels together and then take the average, okay. Yeah, take the average of the 4 labels to be this new field variable, okay, of this iteration, okay. So I go through every site, and then it's called one iteration, okay. So I keep on doing this, 1 iteration, 2 iteration, 3 iteration, and so on, okay. Yeah, and then eventually, okay, after some iterations, okay, then the difference between the field at the center and the average of its labels becomes smaller and smaller and smaller, okay? So that means it is approaching the status, okay, the limit, okay, satisfy this Laplace equation, okay? So I can compute, okay, what's the knot of the error, okay? So this is the Laplacian phi, okay, the knot, okay, because I want this to be 0, okay, but actually it could not be exactly 0 because we are using numbers, okay, and the number always has a numerical precision, okay, with a limited precision, okay, yeah, so that means Laplacian phi could be small, but not exactly 0, okay, but as long as it's more than our acceptance criteria, and that's okay, okay. So if the Laplacian phi the knot, okay, because this is a vector, okay, this is the d, okay, d phi, okay, so phi is a vector, d is a matrix times a vector is a vector. So the knot of this vector, okay, and this is called the error vector because this if it's 0, okay, then it's exact, okay, okay. So now I compute this, okay, this amounts to this, okay, yeah, because this is the you can imagine, okay, this is a vector, okay, the whole thing is a vector. So some of this vectors elements okay, at each side, absolute value square, and then sum over all sides, okay, sum over all elements of this vector, okay. So this is the dot product, okay. So this vector, okay, yeah, and then take the square root, okay. So the knot of A equal to A dot A, okay, take the square root, okay, and then this is the exactly this operation here, what it means here, okay. And then Laplacian phi, what's this? Okay, it will, yeah, it's easily, you can obtain this in the iteration here, okay. Since you're updating, okay, the phi, updated phi, okay, is equal to the average of the labels, okay. So that means you can always use the phi I plus 1 minus phi I, yeah, absolute value square, and then that's the Laplacian phi, okay. Yeah. Yeah, if we exactly satisfy this equation, then Laplacian phi will be 0, okay. Otherwise, okay, the difference, okay, here, the the difference, okay, between the next iteration and this one, the present one, okay, is this phi I plus 1 minus phi I, okay, and then sum over all the sides, okay, yeah, and at each side xy, and there's the Laplacian phi xy, okay, yeah, okay. So this is the knot, okay. So this is the knot of the area vector, okay, or the knot of this the Laplacian phi, okay. And the iteration will stop, okay, if it satisfies some criteria epsilon. Epsilon is something I can specify. Say how accurate you want your solution, okay. Say usually epsilon is say 10 to minus 12, okay. So, yeah, then you converge, okay, yeah. But if your lattice getting larger and larger, okay, then 10 to a minus 12, okay, may not be converge. It may not converge to 10 to minus 12 because the numerical precision, okay, yeah. So in that case, okay, you may need to use the say the double precision or even higher precision representation in order to go to such a high accurate solution, okay. Yeah. So all these are the extension, okay, you can always try, okay, yeah. But if the lattice is getting very large and you want epsilon to be very small, then the problem will be takes a long time to to compute, okay, yeah. So that's turns out to be a very large scale computation, okay, yeah. Okay. Any questions so far? Yeah. Yeah. Here I have more explanation about this knot here. So in general, to solve a linear equation Ax equal to B, okay, by the iterative method, okay, the convergence of the X convergence, say, of this solution vector, okay, X is the criteria, the residue. Okay, so this R is the residue vector because AX minus B, okay, is 0, okay. So this is the, yeah, if you want to see what's if X is exactly satisfied this equation, then this is 0, okay. Otherwise, there's the residue, there's the error, okay. So this is called the residue vector. R is the residue vector. And the knot of the residue vector is called the residue. Okay, so yeah, knot of the residue vector. Okay, R, the knot of the R. Okay, less than epsilon. Okay. So for the Laplace equation, okay, Laplacian phi is equal to 0. So the right-hand side is 0. Okay, so this AX itself, okay, is the residual vector. Okay, A corresponding to the Laplacian. Okay, X corresponding to the phi. Yeah. Okay. Yeah. So this is the algorithm. Okay. So this is an iterative algorithm. Okay. Yeah. Any questions?
Yeah. I have one question.
Yes.
Just a basic one. So sorry. So regarding the equal sign between the two square root, is it an approximation specifically to this Laplacian problem, or is it applicable to other kind of problem?
Yeah, it can be applicable to any other problems. Okay. Yeah, okay. But in the other case, okay, you have to also because when you have the ax minus b, okay, so yeah, this is the ax and then minus b, okay, yeah, so you have to compute this, okay, yeah. So yeah, you might just in that case, okay, you have to have your suppose the okay Laplacian, okay, phi, okay, equal to rho, okay, then you can just use the Laplacian, okay, apply the Laplacian, use the Laplacian, okay, that means this is the formal definition of Laplacian, okay, okay. Mm-hmm. So you can just this minus this, okay, and then see whether it has satisfied the rho, the right hand side, okay, yeah. Yeah, in this case, okay, because I don't have the b, b is the 0, okay, so I can just use this, okay.
Okay, thanks a lot.
Okay, yeah. Okay. Now, how can I implement the iteration? Okay. So the iteration is this, okay. This is the recursion relation, okay. So from I equals 0 to any I, okay. Yeah. So this relation between I and I plus 1, okay. Yeah. But we do not need to introduce too many vectors in order to represent the different iteration, because I always need the two vectors, okay, between successive iterations. Okay, yeah. So that means I just use two arrays. One I call the new, the other called the old. Okay, and then I switch the role. Okay, such that when the thread is using a logical thread. Okay, so this thread is true, then the O is equal to phi 0. Okay, yeah, and then phi new is equal to phi 1. Okay, and then now after I finish this computation, finish this update, then I turn the thread from true to false. Okay, and then in that case, then I will update the phi new. Okay, phi new will be the phi 1. Okay, yeah, and then I compute the phi O. So that means here I always update from the O to new. Okay, and for this case I always update from the new to O. Okay, so this flip-flop. Okay, so that means I can always using two arrays. Okay, to implement implement this recursion relation. Okay, yeah, this iteration. Okay, so yeah, you see, yeah, it's easy to understand, right? Yeah. And then now, how can we update the I mean the field, okay, at each site, okay. So in that case, then I use each thread, okay, handle the updating at each site, okay. So each site, okay, I just use one thread, okay, yeah, okay. Then, yeah, I can decide the block size and then what's the grid size, okay, and then do the updating, okay, yeah. The lattice could be very large, okay, yeah, but it does not mean you have to have the grid, okay, large enough to fit the entire lattice, okay. In the case when the lattice is too large, okay, yeah, you just make your declare your block size and then the grid size, and then that's it, okay, yeah, yeah, the rest just up to CUDA to compute it, okay. But each thread, okay, has to be handled updating at each site. Yeah. Yeah. Okay. Now, then after each iteration, okay, then I have to decide, okay, whether the solution is converged to the desired accuracy or not. Okay. So I have to compute the error vector of the error, okay, the Laplacian phi, okay, at each site, okay, each site, okay. So each site, then I have to compute this, okay. Yeah, so the error each site, okay, is this, okay, yeah, yeah. So this is the sum of the error of all sites, okay. But then first I have to compute the error at each site, okay. Yeah, so this is the iteration, okay, I+1 iteration, and this I iteration, okay, and their difference, absolute value square, okay. So this is the error at each site, and this is computed by each thread, okay. But then I need to sum all of them, sum over all the size, and the square root. So, yeah. So for the partial sum of that means partial sum, there is the partial errors of each block, okay. Then I can do the partial sum of each block, okay, first, by using the parallel reduction, okay. So this, I already talked about this last time, okay. Yeah, so the trace, okay, of a vector, for example, okay. Yeah. So now I can use the parallel reduction, okay, to sum of the errors of each block, okay, or all sides of handled by each block, okay. And then sum all the errors of all blocks, okay, obtained by the CPU, okay, yeah, okay, okay, and this is similar to the parallel reduction, okay, yeah, of the trace of a matrix, okay. In this case, the matrix is this Laplacian phi, okay, yeah, or this vector, okay, yeah, yeah, sum of actually this is sum of all the absolute value square of all elements of a vector, okay, yeah, and then yeah, take the square root, okay, so yeah, the complete code, okay, the sample code, okay, yeah, is in the directory here, okay, yeah, you have to copy if you want, you have to copy this entire directory, okay, to your home directory, okay, yeah, yeah, I'm not going to do the copy for every one of you, okay, you have to copy yourself, okay, yeah, yeah, you want to yeah, edit this code or change this code or do any tests you like, okay, yeah, so yeah, this the entire treatment, entire computation, okay, can be generalized to the Poisson equation, okay, So the Poisson equation is different from the Laplace equation. Is the right-hand side has the charge density, okay? So this charge density can be very general, okay? Yeah, as any charge density you like, okay? Yeah. For the if you want to get an X solution, okay, the charge density has to be some simple form, okay? Yeah, the line charge or point charge or whatever, okay? Yeah, but for numerical solution, okay, it doesn't matter. You can imagine any charge density distribution you like, and then you would just go ahead to you would just compute, okay? Yeah, without any difficulties at all. Yeah, yeah, because the algorithm, the code, okay, presumably can work for any charge distribution. You just specify what is the role this vector, okay. So for the point charge at the site x0 and y0, okay, then the charge density will be a direct delta function, okay, yeah. So so the at x equal 0, x equal to x0 and y equal to y0, okay, then the charge density is q. Anywhere else is 0, okay, yeah. Yeah, but this is in the continuum, okay, yeah. So on the lattice, the direct delta function has to be expressed in terms of the Kronecker delta function. Okay, so this delta x minus x0, okay, is on the lattice is replaced by delta Kronecker delta x comma x0. Okay, so that means when x equal to x0 is 1, otherwise is 0. Okay, similarly for the y. Okay, but you have to divide by 8. Okay, yeah, such that when a equals 0, then this goes to the direct delta function. Okay. Okay. So this summation over all lattice site, okay, amongst the same as the direct delta function integration over the entire volume. Okay, the same. Okay. So there is reason why this has to be divided by 1 over a here. Okay. Yeah. Okay. In the limit a equals 0, then this will go to infinite. Okay. Yeah. So this is similar to the behavior of the direct delta function. So to solve this equation is easy. Okay, you just have to add this term here. Okay, so that means you don't have to change anything of this equation except this term. Okay, you have to add this term here. Okay, so when x equal to x0 and y equal to y0, then you have to cube this term. Okay, so you have to add this contribution. Okay. Otherwise, okay, this term is the 0, okay, so same as the solve the Laplace equation, okay. So only when you come to x0 and y0, then this term has the contribution. Otherwise, no, okay. Yeah, but in general, okay, if you have a general charge distribution, then you could be many points, okay, rho is non-zero at many different points. Then you have to specify, this will be have a taken into account at many different x and y. Okay, so it's easy to generalize. Yeah. Okay. Now, so this is the question you asked. Okay. Yeah. Yeah. So if you have the right hand side, okay, is the rho. Okay. Then here, so this is the Laplacian phi minus rho. Okay. Yeah. Again, okay, this amounts to this. Okay. Yeah, because this phi I plus 1, okay, and the phi I, okay, yeah, both have the rho in there, okay. So the rho are just cancelled, okay, at the difference, okay, yeah. So that means, yeah, yeah, so the actually the knot, okay, is the same, okay, in this case, okay. Yeah, but in general, okay, if you have any other matrix, then you have to, if you put everything on one side, okay, instead of you have this here, the phi I plus 1 equal to average of the labels, okay, then the difference, okay, yeah, could be easily generalized, okay, to any other cases, okay, instead of, if you have you see, this is not the Laplacian phi, okay, but this minus this, or 4 times this minus this, okay, yeah, is the Laplacian phi, okay, so yeah, again, okay, yeah, doing this is among to doing this, okay, so yeah. Okay. You see this term here only make any difference at the point when x0 equal y0. Okay. Yeah. Any other points, this term does not have any contribution. Okay. Yeah. But the term, but at that point, okay. Yeah. The previous iteration and the yeah, and this iteration, okay. Yeah. Yeah. Actually, okay, here, yeah, because phi I plus 1 is coming from this, okay. So you have this phi I plus 1 minus of the phi I, okay. Then phi I also has this contribution there, okay. So that means that this term is cancelled, okay. Yeah, yeah, between the phi I and the phi I xy and phi I plus 1 xy, okay. So this term does not appear in this equation here, okay, in this expression here, okay. Yeah. Any questions about this? Yeah. Okay. The code, okay, for the CPU code, I think maybe I just go to a code directly, okay, rather than using the transparency, okay. Yeah. Here this is the okay. Maybe I go through this first, and then I go to the code, okay. With go using the terminal, okay, and then you can see the code, yeah, in more details, okay, yeah. So this is the CPU code, okay, yeah. First, I have to declare, I mean, two vectors, okay, h new and h old, okay, and then the size, okay, is the nx times ny, so many elements, okay, yeah, and they are full, okay, data type is full, okay, yeah, and then I set all the values to 0, okay, yeah, it does not necessary to set to 0, okay, you can set that randomly, it's fine, okay, yeah, but then you have to impose the boundary conditions, okay, yeah, for example, yeah, for my boundary condition is easy because three sides are 0, okay, only one side is 1, okay, at the top, okay, it's 1, okay, so I just set this to 0, or fill entire array, okay, to be 0 first, okay, and then I set the top boundary, okay, to be the phi is 1, okay, so so this is the how I have the entire yeah, array, okay, at the fixed y, okay. The fixed y is the ny minus 1, okay. Yeah, y is equal to ny minus 1. And x, okay, go through all the x, okay, yeah. So these sets impose the boundary condition here. Okay, here, okay, so here, this is 1, all other sides are 0, okay. And then initially I set all the field, okay, on each side to be 0, okay. Yeah, and then I set all the field here, okay, to be 1, okay. And since I have using two arrays, phi new and phi old, so I have to do the same for both arrays. Okay. 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 Yeah. Here. Okay. And then error is the criteria, the stopping. So this is the error. First, this error denote the error, okay, from the Laplacian, okay. And epsilon is the stopping criteria, is supposed to be a small number, 10 to minus 10, 10 to minus 12, okay. First, I say the error is large enough such that it can proceed the iteration, okay, without going out to the loop, okay. So initial iterations 0, and then remember I have to use a logical thread, okay, yeah, and I have to declare this as a Boolean variable, okay, to be true, okay, and then when I finish one iteration, I will turn this to false, and then the row of the new array and old array is flipped, okay. So update the new from old or update the old from new, okay. Yeah, depends on the thread whether it is true or false. Okay, and then there's a top, left, right, bottom, okay. These are the few variables of the label, okay. Yeah. Okay. So now if the error is bigger than the stopping criteria, okay, bigger than then the proceed to the iteration, okay. And also I have to specify the iteration cannot be bigger than some maximum iteration, okay. Yeah, this is just safeguard, okay, any bug in your code, okay, you will not go forever, okay. Yeah, so it will stop no matter whether it converge or not, okay. Say this 100,000, okay, yeah, or whatever the number, okay, you want to set in, okay, but 1,000 or 10,000, okay, yeah, such that your program will stop after so many iterations, okay, yeah. Yeah, usually it would not take too many iterations, okay. So if the iteration goes too large, that means there must be a bug in your code, okay. So now if this thread is true, okay, then I would update the array O, update the array new from the O, okay. So that means now this O, okay, and then I have this computer site, okay, it's labels, okay, x minus 1, x plus 1, y minus 1, and y plus 1, okay. So y, okay, this is a one-dimensional array, okay, but it's represent the two-dimensional lattice, okay, and according to the numbering scheme, okay, I use, then each change of y will change the side number by nx, okay, so y minus 1 will be minus nx, okay, y plus 1 will be the side number plus nx, okay. For x, okay, just minus 1 and plus 1, okay, yeah. Yeah. Here, the iteration excludes the boundary condition. That means if x is 0, y equals 0, or x equal to nx minus 1, or y equal ny minus 1, they are the boundary, okay? So do nothing to the boundaries, okay? Yeah, because the boundary has been set to the fixed phi, okay, fixed value, okay, in the beginning, and then within the loop, the iteration, okay, yeah, the boundary is not changed at all, not updated at all, okay, because it's fixed boundary function. Yeah. So then I know the side number of the is left, right, bottom, and the top. Yeah. So this is the bottom, left, right, and top. Okay. So y minus 1, x minus 1, x plus 1, and y plus 1. Okay. So with these values, okay, B, L, R, T, okay, bottom, left, right, and top. Okay. Yeah. And then using the average, okay, that means this divided by 4, okay, that's 0.25 times it. And update the phi at this side, okay? Yeah. The psi is x plus y times x and x, okay? Yeah. Okay, now I get the new the phi I plus 1, okay? So the difference between the previous iteration, phi I and phi I plus 1, okay, is this, okay? So the difference, okay? So the error of this at this site, okay, is this difference, the difference square, okay, yeah. So this is the error of the square, okay, of the difference, okay, yeah. So this is the yeah, the error, and then yeah, for the CPU, okay, you have the do loop, okay, then you just go for all the size, and then that means that eventually this error will be sum over all size, okay, yeah, sum over all size. Okay, so this is the error of this iteration, okay, after this is finished, okay, yeah. Now, else, okay, if the thread is true, then I do this. If the thread is the false, okay, yeah, then I would do this. Update the O from the new, okay, yeah. So that means when you have a thread, when the thread is the true or false, then either one, you only execute either one of the either update from the new to O or update from O to new, okay, either one of them, okay. So this part is exactly the same as the previous one, except you exchange the role, okay, of new and O, okay, yeah, here from the new update the O, okay, okay, okay. After this update, then I turn the thread, okay, true from false or false from true, okay, using this, okay, not the thread. And then iteration number increased by 1. And then for this iteration, then I compute the error, the knot of the error. So I take the square root, okay, of the sum of all the difference square over all, sum over all sides, okay, and then take the square root, okay. So the iteration will stop, okay, yeah, if the error less than the epsilon, okay, less than the stopping criteria, okay, say 10 to minus 12, okay, and then stops, okay, and then that's the solution vector, okay, the solution of the field, okay, solution of the Laplace equation or Poisson equation, okay, yeah, yeah, either it is a solution or you have a bug in your code, then when the iteration is exceed the maximum number of iterations, then you exit, okay, but it does not give you the correct answer, okay, if you have a bug in your code, okay. Okay, so this is a CPU code, okay. Now let me go to the sample code of the CPU code, okay.
老师，
Question. Yeah.
老师，我有个问题想问哦，在你的程式码当中，你记录那个 YMP1 跟 YP11，它是用 site 加减 nx 对不对？
Yeah.
可是这样子遇到边界的时候，不是会产生那个
对，但是这个不在边界 ，OK。You see, not the boundary is not excluded, is excluded, so I don't have the boundary problem, OK? Yeah.
但是你的那个，当你的 xy 等于1的时候，那这样你的这样你的 nx 也不会等于1啊，所以当你的 xy 的坐标来到1的时候，那这样
没有
ym1 就会变成
You see, there's a condition here. You see, if x equals 0, or x equals nx minus 1, y equals 0, or y equals ny minus 1. Okay, so these are the conditions you are considering. Okay, but they has already do nothing to it. Okay.
对，这个
Any other size will be okay. Okay. Right.
我的意思，我的意思是，假设现在 x 跟 y 都是1，然后你的 nx 假设是5好了 ，ny 也是5，就是。
好 ，nx equal 1，OK fine，OK。
对，
nx
好，那这样
没有 nx 不是 1，OK，nx 只是 nx，OK，yeah，you know？
我的意思是说，假设现在 x y 都是1，然后
x y equal 1，nx
跟 ny 都是5。现在是这样的条件下，那这样你的 site 它就会等于，site 会等于6嘛？就是1加5等于6。
所以这个就没有问题啊，没有问题啊。所以你看，假如的 x 1，
对，没有问题。
go back here，go back to the lattice，OK？Yeah here。你讲是这个 site 对吧？You are saying this site, right?
Yes.
Now its neighbors at these 4 points, okay? Right?
Yes.
And then there's no problem of it, right?
对耶，好，没有问题。
是这样，所以是没问题的 ，OK。除非你是照这边来 ，OK。Then you can kind of problem because the level, you see the bottom of it, okay, will be this side, okay. But yeah, this is on the boundary, okay. So I don't need to worry about it because when you see this here, the condition here already excludes such a, you see, if this are satisfied, then do nothing of it, okay. Anything else should be fine, okay. Right?
Yes. Okay.
Yeah. Okay. Finally, you see it. Okay.
Thanks.
Yeah. You see, we will come to this problem when, say, when we have a lattice, say the torus. Okay, the lattice on the torus. Okay, then there's no boundary at all. Okay, then in that case, okay, when I go through the boundary, then I have to mold it. Okay, and then I will discuss that later. Okay, when I talk about the Ising model. Okay. Yeah. Okay. So for this with boundary, okay. Yeah. And once I specify this, then no problem of this this 4 line here. Okay. Yeah. Okay. Yeah. Now let me see. Any other questions? Okay. Okay. Let me go to the code. Okay. Yeah. I hope it's still it's still connected. Good. Okay. I should go to here. No, this one. Okay. This one. No. This terminal. I have too many terminals here. I have one already. Okay, so let me exit the loop here first. Okay. I changed it to home. Okay, here. Change it to the home folder 2024. Okay. Oh, about your username, okay, your account, okay. here, this A, B, D, F, these are the NTU students, okay? And there's no string in front of it, okay? But if you are from NTNU, then there's a string NTNU underline, and this your serial number at NTNU, okay? So for the student NTUST, okay, then you have this string in front.
老
And
师，你
then
没有切换你分享的画面。
okay, sorry, yeah. Yeah, I forgot. Yeah, sorry. Let's see. Yeah. Okay. Let me see. Yeah, you have to correct me. Yeah. Okay, now you see it, okay? Yeah. I just talked about your username, okay, your account in TLCP1, the GPU cluster, okay. For the NTU student, okay, and your account always start with a letter, okay, and the must be the capital, okay. Yeah, usually you have the just the lowercase, okay, and for the account here always the uppercase, okay, yeah, letter, and then this is your student number, okay, except the first letter is the uppercase, okay, yeah. For the NTNU student, then you always start with this string NTNU underline, and then this is your student number. For the NTUST, okay, students, okay, you have this, and then the underline, and then this is your usual student number, except maybe the first letter here is also the uppercase, okay. So, yeah, and your first time password, okay, is exactly the same as your student number, the entire student number, okay, yeah. After that, okay, you have changed your password, and then you have to remember it, okay. If you forget the password, then I can reset it for you, but I presumably you should remember your own password, okay. Okay, and you can only execute the control job, okay, under this directory, okay. That means under your home directory, okay, yeah. So home CUDA 2024, and then your home directory, okay. Everything under your directory. Then you can submit the job to the console in any other directory, okay. But you don't have any other directory to open, so that's fine, okay. As long as you are in a home directory, then there's no problem, okay. Yeah. For me, okay, I have more directories, okay. So I need to put my code to this directory in order to submit the job to Condo, okay. Yeah. So there's a usage.x in the home. Every sample code actually is in here. CUDA home CUDA lecture. Okay. CUDA lecture. Okay. Yeah. Here. You see, the usage dot txt is the the description of how to use the GPU cluster. Okay, and then each directory is the sample code. Okay, according to its different yeah. Yes, this is the same as described in the lecture. Okay, yeah. So today's sample code is all in the LaPlace and then tag. Okay, why there's a tag? I will tell you. There's the for the texture. Okay, using the texture. Okay, yeah. Okay. Let me go to the code. I have to go back to my Okay, here. So in my home directory, I have the CUDA lecture. Okay, actually, this CUDA lecture is the more or less the same as the what has been put on the CUDA lecture underline 2024 under the home. Okay, so I will first put I have my code developer here, and then test one here before I would post it to the home CUDA lecture 2024 directory. Okay, so first let me look at the Laplace CPU. Laplace, yeah. Okay, yeah. This is the CPU code. Okay, yeah. But I also use the extension CU. Okay, because I just use the timer of the CUDA timer. Okay, yeah. I do not have to use the CUDA timer. Okay, but just for the conform. Conform with the other codes. Okay, so I just use the same timer. As I already showed you, okay, the timer included this actually give you the same timing results. Okay, by the GCC GNUC timer. Okay, yeah. Okay, here is the maximum iteration. Okay, you see, I put a very large number of iteration. Okay, yeah, but usually it does not take so much. It does not see such a large number of iteration to attain the stopping criteria, the accuracy. Okay, yeah. So I have have the two vector. Okay, one is a new, the other is old. Okay. So first, just enter the size of the lattice, and then that's it. Okay, and then the total number of size. Okay, yeah, this nx times ny. This is size. Okay, is the times the size of the fold, and then declare this array. Yeah, x new and x o. Okay, and then set all of them to 0. Okay. Now, yes, this is of course equivalent to doing this this for loop. Okay, but yeah, this is more efficient. Okay, yeah, mem set. Okay, set it to the same value. Okay, yeah, right, and using this. Okay, so I comment out this. Okay, but just show you. Okay, yeah, they are equivalent. Okay, but usually this is faster. Okay, using the mem set. Okay. So initial the boundary condition. Okay, initial the field vector with the boundary condition. Okay, yeah, and I will write the initial vector. Okay, see whether the initial field configuration is the same as what I specified. Okay, yeah. So the so this is the I just print out row by row. Okay, yeah, according to the picture. Okay, same as the picture convention. Yeah. And also echo as well as yeah, to the screen as well as right to the file. Okay, so this is the pin out on the screen. Okay, yeah, in the monitor. Okay, and create a timer. Okay, and then the compute the reference solution, because this is the one I put in the GPU code too. Okay, so compare the CPU solution and the GPU solution. Okay, so I call this a reference solution. Yeah. And then first I declare the error is 10 times of larger than the stopping criteria. Okay. Then the iteration will proceed. Okay. and set the initial counter for the iteration. Okay. Yeah. So this is the two different iteration. One kind is the when flag is equal to true, then I update the new array from the old array. Okay. So H new is I plus 1, like HO is I. Okay. Yeah. When the flag is equal to false, then it could execute this portion. Okay. And then in that case, okay, I update the O from the new. So the row HO is HI plus 1, and this is the HI. Okay. Phi I. Okay. Yeah. Okay. And in both cases, okay, I also compute the error. Okay. Yeah. After this is executed, then I would turn the flag, okay, to opposite, okay, from true to false or from false to true, okay. And then the iterations at 1, and then compute the knot, okay, the knot of the error, okay, yeah. And then you would do, and you come to this again, come to this here, whether the this condition is satisfied, okay. Yeah, if not, okay, that means when the error is less than the stopping criteria, EPS epsilon p, yeah, then it will exit, okay. Then you would exit the while, okay, and then we'll pin out, yeah, and then yeah, the error, okay, and then the exit, okay, new exit, okay, yeah. So exit if the error less than EPS or the iteration is bigger than the max, okay, then pin out the error and then the total iterations and stop the timer, okay. Then obtain the time, the total time, okay, in terms of milliseconds, and then convert it to the flops, and then convert to the gigaflops, okay. So the number of flops is how many iterations, and then there's a total operation is say 7 times the number of the size inside the in the boundary, or not in the inside the boundary. Okay, so the boundaries you don't need to update. Okay, only so this is the nx minus 2 times ny minus 2. So that is the total number of sites to be updated. Okay, and for each updating of each site, it requires 7 flops. Okay, 7 floating point operations, which you can easily count. Okay, yeah. And then you can easily convert to the gigaflops. Okay. And then after that, destroy the timer. And then output the field configuration. Okay. So the 5 CPU and then the final field configuration. Okay. And then print out on the screen as well as print out to the file. Okay. So make, print, make. Okay. Now, so the input CPU, okay, CPU, okay, here is only 8. Let me change it to the 1010. Okay, so this is the similar to this, exactly the same as in the transference of my lecture. Okay, so let me use the 1010. Okay, yeah, actually I can just do it. Okay, here. Okay, here. I do not need to submit to a condo because I can just use the CPU of the node, okay, to do it. Okay, so yeah, so I can just do it on the console here using the Laplace CPU. The input CPU. Okay, you see? Yeah. I just using the CPU of the T12 CPU1, the head node of this GPU cluster. Now, it took 256 iterations, okay? And the processing time is too little, okay? Then I even cannot measure the time, okay, in milliseconds, how many milliseconds, okay? So this is the initial field configuration. You see, this is the 1 here, and all others are 0, right? You see? Okay. And then this is the solution, okay? That is not a very precise number, okay? You see, this is only up to 2 decimal place, okay? Yeah. Yeah. Yeah, just 3 significant number, okay? Yeah. And then you can see, okay? But you can see the train of the solution vector, okay? Because it's the high here, okay? So the boundary here is the 0, okay? So the field must be going from high to low, okay? So we can see it's decreasing here in this direction, okay? Right? And so it's here decreasing. It's decreasing, okay? Okay. Now, since this is 0 and this is 0, okay? So, and you can see, okay, the boundary here and the boundary here is the same, okay? So there must be a symmetry, left-right symmetry, okay? So this color, the solution vector here, must be the same as the solution vector here, okay? You see? Here and here is the same, okay? Here and here is the same. This and this is the same. So you see, it's satisfied the symmetry, okay? If not, okay, there must be some error in your code, okay? Yeah. Yeah, because the problem initially, the problem has to have the left-right symmetric symmetry, okay, parity, okay. So your solution must also obey the parity, okay. Yeah. So you can see, okay, just by looking at the solution vector, you know whether it makes sense or not, okay, it's reasonable or not, okay. Yeah. Okay. Yeah. Any question about this? So this is the most simple example of the solving the Laplace equation on a very small lattice, and it takes no time to do it. Okay. Of course, I can do it with a larger lattice. Okay, but then for larger lattice, then you would take longer time. Okay. Yeah. Say 128, for example. 128 and 128. Okay. Yeah. Yeah, it's still very fast, right? Yeah. Yeah. And the let me see. I have to find out what's the let's see. This is the solution, right? It's so fast. Okay. I even could not see the timing. Okay. Yeah. Because it's a row, so I have to put it to the output. Okay. I have to edit it. Okay. Okay. Yeah. Otherwise, it takes. Okay. Then. Okay, you see, it's very fast. Now, since it output the field vector, okay, so the file would be large. Okay, yeah. So this is the initial field configuration. Okay, it's 128, so very long. Okay, yeah. So this is a solution vector. Okay, solution, yeah, field configuration. But let's see, what's how much time? Yeah, okay, I miss it. Okay, you see, time is 0. No, I think I have to use the CUDA in order to, yeah, otherwise, yeah, this is not exactly the CPU, okay, because this is the CU code, okay, so, yeah. So I do not get the timing, okay, yeah. Then I have to turn to the GPU code, okay. Yeah, let me go to the GPU code first, okay. Yeah, before I can do the demonstration, okay, yeah. Okay. Let me switch the sharing, okay, yeah. Switch the screen, okay, yeah. Okay. Let me see. I have to share another screen. Let's see, where is it? Oh, here. Okay. So let me turn off the banner. Okay. Okay. Now for a GPU core. Okay. So GPU core is not much different from the CPU except this basic ingredient. Say you have to specify you see this kernel, okay? Since I use the parallel reduction, okay, so I have to declare the share memory, okay, the size of the share memory in order to do the parallel reduction. The sum of the error of the size of handled by one block, okay? So the difference, okay, yeah, is the difference of the phi I and phi I plus 1, okay, at each side, okay, or handled by each thread, okay. Yeah. So there's the NX, okay. Yeah, the and NY, okay. So now I assume the entire grid, okay. Yeah. I mean the lattice, okay, can be put on the one grid, okay. Yeah. So X, okay, and Y, okay. Yeah. So any side, okay. Yeah, is I have this two-dimensional block, okay. So yeah, and this is the side X side, and then in terms of the Fed index in the X direction, okay, and then the Y, okay. So and then the cache index, okay, yeah, is the Fed index X plus the Fed index Y times the block dimension, okay. So each thread of the block has a cache index, okay. And the size is X plus Y times NX, okay. Then I give on the boundary, okay, then the difference is 0, okay. Yeah. So so when I specify the block, okay, yeah, some of the blocks, maybe have the boundary, okay, maybe have one side, okay, coincide with the boundary, okay, or two sides coincide with the boundary, okay. Then if the thread, okay, itself is at the boundary, okay, then it does not do anything, okay. So the difference 0, okay, yeah, because it's not updated. The 5-year value at that of the site, okay, handled by that thread, okay, is not updated, okay. So the difference 0. Else, okay, do the following, okay, is x minus 1 and x plus 1, y minus 1 and y plus 1. And then if thread is equal to true, then I update and find new from the find old, okay. Yeah, otherwise, if the thread is false, okay, then I update the find old from the find new, okay. And in both cases, the difference is the find new minus find old, okay. Yeah. And then there's so the difference square, okay, would put to the shared memory, okay, such that, okay, every thread of this block can see this, okay, can get this difference square such that I can do the parallel reduction, okay. Yeah. So every time I use half the number of the IB, okay, yeah, half and half, and so on, okay, of the total number of threads of this block to do the addition, to do the merging, okay, to do the reduction, parallel reduction, such that at the end, the sum of all the different square, okay, of this block is at the thread ID 0, okay, is the thread ID 0, and then the sum of the difference square of the entire block, okay, yeah, would go to the is in the cache at 0, okay, and then go to this, okay, the sum of the different square of this block, okay. Okay, so here is the main code. Okay, in the main code, I specify the say once the block size is determined, okay, is fixed, then I have to declare what's the size for the shared memory for doing the parallel reduction. Okay, yeah. So so this is the kernel Laplacian, and then I have to specify the grid size, say how many blocks and how many threads, the block size, and then the size for the shared memory. Okay, yeah, and then and also there's a thread and notice. Okay, and then the copy. Okay, after it's done, okay, then copy the C. Okay, yeah, from device, okay, to host. Okay, and then the host, okay, will do the sum of the different square of all blocks, okay, and then this will be the different square of all sides, okay, of the lattice, and then take the square root, and then that is the knot of the error, okay, knot of the error vector, knot of the residual vector, okay, and then after that, the iteration is increased by 1, and then the thread is increased. Each thread is changed to from true to false or from false to true. Okay, and then do this iteration. Okay, so
excuse me.
Yes.
What if one index, the neighbor of one index is cross to other block? Could I do if the neighbor is in other block?
Once it is one, then that for example this, okay, this is always applied to every thread. Okay, so this condition, okay, if this thread, okay, belongs to this or this, then you will not do anything. Okay, just the 0. Okay.
Yes, but perhaps the name, the XML and SM1 and XP1, that one, maybe the site plus 1 is will go to another block. right?
Go to another block.
Maybe the matrix is the lattice is too big, then
Yeah,
it is cross multiple blocks. Then what will it do?
yeah, this is okay. This is okay because it's in the global memory. Okay, so every thread, okay, can read everything. Okay, on the global memory. Okay,
so the file old is in the global memory.
In the global memory. Okay, yeah.
So what will be stored in the local memory? Which? Okay.
So every block, every thread can access the file old and file new. Okay, yeah. So yeah.
So will it be faster when we put the file? We cut the file into the local memory. Will it be faster?
Local memory, I think it's not large enough to accommodate this array because this array sometimes is very large. I cannot put to the say the shared memory or anything like that. Okay, and not yeah. So yeah, this is the most we can do is the shared memory is in the global memory. Okay, because it's a large memory. Okay, yeah, it could be say yeah as large as 6 GB in the case of the GTX 1060. Okay, so yeah, so it's important to put on to each block. Okay, each block only has a limited amount of memory, say the register, and then the share memory. Okay, and that's it. Okay, yeah.
Okay, thank you.
Okay. Actually, we can because there's have the read from to the read and write to the global memory. Okay, and this is the bottleneck. Okay, but as long as your commutation, okay, is shared, yeah, is much more than the communication time. Okay, then the GPU will be very efficient and much faster than the CPU. Okay, that means when the block size is getting very large, okay, or the data size is getting very large, okay, yeah. Another way to speed up the access of the global memory is through this special reading cache called the texture, okay. This I'm going to talk about it, but I think I do not have enough time to do it this time, this lecture. Maybe I have to do it on the next lecture, okay, yeah. So, but let me go to the GPU code, okay, first. Yeah. Let me switch the screen. Okay. Let me go to the another screen to the terminal screen. Okay. Yeah. Okay. Yeah. Every time you would want me. Okay. So this is the Laplace .cu. Okay. Yeah. So the HU and HO are in the host. Okay. And there's a device vector also the HNU, DNU and DO. Okay. And then there's a DC. DC is the array holding the sum of the different square of each block. Okay. And the maximum iteration and then the stopping criteria. Okay. So this is the kernel. Okay. Yeah. The GPU kernel. Okay. Laplacian. Okay. Yeah. With the phi O, phi new, and then the C and the Boolean thread. Okay. Yeah. So Boolean thread is set by, is controlled by the host. Okay. After one iteration, then it will change the thread. Okay, from true to false or from false to true. Okay, and then compute the error. Okay, the knot of the error vector. See if it is satisfied the stopping criteria. Okay, it satisfies stopping criteria, then you stop. Okay. Okay. So once the stopping error, okay, is bigger than the stopping criteria, and then you would call the Laplace, the kernel, okay, to go to each iteration, okay. So that means the Laplacian is only just doing the one iteration update, okay, yeah. And you could update from new to old or from old to new, depends on the inputting thread, okay, the logical thread, true or false, okay. Here, okay, if thread is equal to true, okay, then update the file new from file old, okay. If thread is false, then update the file old from the file new, okay. So yeah, you see, this kernel, okay, after updating file new and file old, okay, the value file new and file old is the same, okay. It does not change, okay, yeah, okay, such that the next time you update, okay, then the file new and file old can be switch their role, okay, yeah, and you don't have to change be in the file new and file old again, okay. Okay. So now this is the main code, okay. So this is the just some center reading the input, and then this is the GPU ID, okay, and then lattice size, and then the specify the block size, number of threads per block, okay. So in this case, this is two-dimensional block, so yes, give the specify the TX and TY, and then yeah, since I intend to use the one entire grid to the large screen to one grid, okay, so yeah, just compute the blocks, how many blocks, okay, for the grid size, and then allocate the H file, okay, initialize the vector with boundary conditions, okay, yeah. And then pin out the initial file, okay, and create a timer, okay, and copy the HO to DO, HO, H new to D new, okay, yeah. So this is only for the initial value, okay, yeah. For each iteration, it doesn't need to copy at all because it has been updated. So, and then the device memory, okay, already have the most updated information. Okay, so that means the data of the GPU is persistent. Okay, you will not change otherwise. Okay, yeah, you will not do the iteration with this updating algorithm. Yeah. Here. So while this, and then just call this kernel, okay, Laplacian, okay, and then compute the residue vector, residue, okay, the error vector, the node of the error vector, okay, and then if it's less than the stopping criteria, and then you will stop, and then exit the while loop, okay, and then pin out the error, and then the total iteration, and then stop the timer, and then see how much time it takes, okay, and copy the result from device memory to host memory, and then output the field configuration, okay, the file, okay, yeah, and compute the total time, and then yeah, and for the CPU, yeah, then they feed the HO, H new, and T new, yeah, computed. not to compute the CPU solution, then fear. Okay, to compute the CPU solution, then do this. Okay, so this part is the same as the Laplace CPU dot CU. Okay, yeah. Okay. Okay. Start timer and then compare the CPU time and GPU time. You see the CPU time, okay, since it used the CUDA, okay, so it has to be computed here, okay, right, and stand alone, okay. So so you use the use CME, okay, CMD, okay, CUDA, okay, to submit the job, okay, as a GPU job, okay, then it will give you the correct for the previous code, okay, the Laplace CPU, okay, yeah. Here, since CPU is also code is also computed here, so CPU time is also computed, okay, okay. After everything done, then I have to reset the CUDA device reset, okay. So now let me show you the input. So the input here, okay, this is the GPU ID, okay, and this will be device number assigned by the condo, okay. So you don't have to worry about whether it's a 0 or 1 or whatever, okay. You assign it, okay, and see which GPU is available. Now there are 4 GPUs available. If you use single GPU, okay. Now I use let me see, okay, 8, okay, for example, okay. And then the block size is 4, okay. So this is just a test, okay. So okay. Now look at the CMD file, okay. Now, so for this one, I think you do not need to change because this is the GPU type SM6160G, okay. And one CPU here means that there's a one GPU, okay, yeah. Okay, so this is the initial direction. Okay, this has to be in your home directory. Okay, wherever this code, okay, is there. Okay, so that means you have to use the PWD command in order to get the exact path. Okay, for the working direction. Okay, yeah, yeah. Different people has a different initial direction. Okay, yeah, because it is the job is submitted from different by people, and then the different initial working direction. Okay. So the job argument, okay, is the Laplace, okay, is the code, and then the input and then output. Okay, so I have several different lines here. Okay, so let me comment out this and then just use the simplest one. Okay, okay, now and then okay, so this is the CMD file, okay. Then before you submit a job, you can use the JView, okay, see how many jobs are, okay. You see there's no job is running on this condo system, okay. So I can submit the job now, condo, okay, CMD, okay, yeah. This CMD can be any name you like, okay. You can CMD, blah, 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 so on, okay. This is up to you. But as long as it's in the same format, okay, that's fine. Okay. So now I have to JView and see what is it doing. Okay. Yeah, you see it's still, yeah, it's initializing. Okay. So after I, and then it will be in the one state. Okay, one. Okay. Okay, it already done. Okay, so now let me go to the output. Yeah, output is here. Output the file here. Okay, get the output. Okay. You see the output, we got all the runs with the same name. Okay, so there's some output from my previous one. Okay, so the run from this time is here. Okay, the last portion. Okay, so it was run by the GPU ID 0 with the device ID 0. Okay, and then there's a 8844. Okay, and then this is the, you can see the input time for the GPU, and then the error 0. Okay, yeah, is the total iteration 165, and the time is 1.7 millisecond. Gigaflops is small because there's very small lattice. Okay, so the total time is a 4.17 millisecond, and for a CPU, okay, again the number of iteration is the same. Okay, but for the CPU, okay, the millisecond, okay, is only 0.02 millisecond. Okay, yeah, so it's very little. Okay, yeah. So for this small lattice, okay, CPU is faster than GPU. Okay, okay. But now I can go to a larger lattice. Okay, so you can see the yeah. Say for example, I change the, say this 256. Okay, say 256 by 256. Okay, and then block size is 16 by 16. Okay, and then I have compute CPU solution and then GPU solution, so I can select two. Okay, so you see, you only CPU solution you use 0, GPU solution use 1, and both you should use 2. Okay, yeah, but for the very large lattice, okay, yeah, say 512 or 1024 and so on, then you should not turn on CPU solution at all, because the CPU will take a long time. Then your job will be doing it. Okay, it's not using the GPU, but only using the CPU, and it takes a long time. Okay, so yeah, so the CPU solution only for small lattice to check whether the GPU code works or not. Okay, yeah, and now let me look at the CMD file again. Okay, now let me comment out the other lines here. Okay, yes, and then you see whenever there's this sign here, okay, then you will not read it. Okay, this is only for your documentation. Okay, yeah. So okay, now Quanto submit. Okay, now after submit, you see whether okay, now it start initialized. Okay, and then it takes some time to start. Okay. Yeah, now it's running. Okay, now it's running. Okay, so it's running in the host 218, and then using the GPU. Yeah, and yeah, so this is the working direction. Okay, so now you see, now there's a job running. Okay, so initially the number of GPU fee was 4. Okay, but then after it's running, okay, it becomes 3. Okay, number of free is only 3. Okay, one is busy. Okay, so this GPU is using up one of the GPU, so the system saying that one GPU is busy. Okay, because it's running on this job. Okay, now. Okay, done. Okay, so now let's look at the output. Okay, of the 256. Okay, 256 by 256. Okay, you see. Okay, so this is the most recent computation. Okay, it starts from here. Okay, yeah, actually, yeah, because it's enter GPU ID here. Okay, So now the number of iterations is quite large now, okay, about 125,000, okay, iterations, okay, and the total time is takes how long? Just 2 seconds, okay. GPU processing time is only 2 seconds, okay. Yeah, but it's still more than the output time. Output time is only is 0.2 millisecond, okay. The input time is 0.2 second, okay. Yeah. So so the total time is this, okay. You see the processing time is the dominant part, okay. And the error, okay, in this case is not 0, okay. Yeah, error is 10 to minus 11. Remember, the stopping criteria is 10 to minus 10, so this is less than the 10 to minus 10, so it stops, okay. Yeah, and the CPU, okay, of course, okay, is the number of iteration must be the same, okay. Yeah, because the same stopping criteria, so it must require the same number of iteration to reaching the same stopping criteria, okay. And the time, okay, is more, okay. Yeah, much more, okay. So for this case, okay, the GPU is 9 times faster than the CPU, okay. Yeah, of course, if you have a more powerful CPU, then the speed up, okay, may not be so large, okay. Yeah, but yeah, go to larger and larger, okay. Then no matter how powerful your CPU, then my GPU always beat your CPU, okay. So in this iteration, in this solving a Laplace equation, okay, by the Jacobi method, okay, yeah, turns out to be computationally intensive, and yeah, GPU can give you a good provide you a good platform to do such a computation, okay, yeah, and then you get a large speed up, 10 or even up to 100, okay, depends on the size of problem, okay, yeah. Of course, you can have a large CPU cluster to do it, okay, but then the cost, okay, will be much higher, okay. If you use a CPU cluster, then you have to use the infinite band and all these things, okay. So for GPU, okay, just one GPU, okay, can be, okay. Any questions? Yeah.
老师，我有一个问题，就是你的作业3，我想问一下你的作业3，它的意思是什么意思？对。
Problem set 3, okay, you're talking about. Let me switch back to the problem set 3, okay. Yeah. Let me stop this, and then I back to the problem set 3. Let me first switch the screen to the PowerPoint. And maybe not the correct one, is it? I'm not sure.
现在看到是老师你的档案总管。
档案总管这个不太对 ，OK， 档案总管没问题，我会把它 switch to 这边。Problem set 3, OK。有没有看到？
没有
没有。
对，
没有
看到你的档案总管。
OK， 我再把它 switch 过去 ，OK， 没问题。OK， 我再 switch to 这个正确的这个this one， 有没有看到？没有。
没有。
没有。
现在有。
没有 ，OK，
好。
OK，
好。我想要请问的意思，就是你这一题的意思是要指说，在一个2维的这个场里面的晶格场里面，然后有一个
3维
在3
3 dimension，
哦，好，在三维里边，然后有一个电子在正中心，
对对
然后边界都是在边界的时候，它的那个电量都是零嘛，这个意思吗？
对，phi 都是零 on the surface，OK，phi 是零，就是我的 boundary condition，OK，
都是零，
都是零，OK，都是
然后
zero，
正中心
yeah，all
要是一，
zero，OK，yeah，
正中心
so
要是
the the boundary of this three-dimensional lattice has the phi equal to 0，OK，yeah。
好，那最后面你最后有问一句说，Does the potential approach the Coupler law in the limit L
In
大于
the
大于
limit L much bigger than 1, okay.
对，
So that means in the limit when the lattice becomes very large, okay,
对，那我想
very
问的
large,
就是，
then the of course the Coulomb's law, okay, just fall as a 1 over r, phi is only falling 1 over r, right, and go to 0, right? Yeah.
对，但
So, but if r is big enough, okay, then it will be going to very small, okay. So this is not exactly the same, okay. But so there's this the question, okay. When the L much bigger than 1, okay. So you have many different solutions. L is equal to 8, 16, 32, 64. Then you can extrapolate your solution to L infinite, okay, or as large as you want, okay. Then in that case, okay, then does it give you a solution same as the Coulomb solution, say 1 over r solution, or not?
老师，我想要请问的是，就是我其实不太懂松柏方程它的意涵在哪里，就是我的那个 phi 带进去 xy 带进去的值带出来的结果，那个是指什么物理量？对，我
你说
不懂的其实是松柏方程的意义，
什么松柏
就
分程？
是那个 Poisson equation 的意义。
哦，Poisson equation，yeah，Poisson equation 的话，就是我刚才说的 Laplacian phi equal to rho，OK？
对，我知道它的等式是长这样，但是我不知道它的物理意义，就是它各个物理意义是什么，那个 phi 的单位的物理单位意义是什么，就是我不知道。
phi 的话is a you can regard this as a say electric static potential，OK？phi
就是电量的意思吗？
没有，不是电量，OK？phi 的话是这个，you know what's the electric field, right？OK？
这我不知道，因为我不是物理系的。
哦，不是物理系啊，OK？
对。
看它，我应该let me see. Let me see. Maybe my lecture transparency. So will give you the. Let me see here. Here. Oh, I did not say this. Okay. I will add some more slides, okay, to explain, okay, what's the phi, what's the meaning of phi, and how is it derived, okay? So it's in terms, actually, this is the scalar potential, okay, scalar potential of the electromagnetic field, okay, and this can be obtained from the say the gradient of the phi is equal to the electric field. Okay, yeah. Did you take the general physics before? No.
No.
普通物理有没有练过？
我修的科系没有上普通物理啊。
哦，你没有上普通物理？
对啊。
哎，你是什么系啊？
我是双主修到资工，我本身是学习科学学士学位学程。这个科系他没有修普通物理，然后我双主资工的时候也不需要修普通物理，所以我还没有修过普通物理。
从来没有修过普通物理。
对。
OK，你中学有没有学过物理？
有
OK， 中学学物理可以啊。OK， 好，然后我再加几个 transparent 上去，你应该就不懂了。OK， 我再把这个 transference add 进去 ，OK， 好
好。
，OK。
然后老师，你的作业3的截止期限是今天的下午5点，可以稍微延长一下吗？因为
我没有说是今天下午。
你在作业3的那个 slide 的那个 PDF 底下有写说，submit your
June 11啊，
对啊
，June 11不是 March 11。
哦，对不起。
哦，这个是那个 3 months difference，come on。
哦，对不起，好，没问题的，老师。
June 11是这个是期末 ，OK。实际上所有 problem set 就是期末才是 deadline，OK。
哦，好，对不起，老师。
不要紧张 ，OK， 不要紧张 ，OK。Yeah, OK.
Professor.
Any other questions? Yeah.
Professor, yes, I have a question.
Yes.
I want to ask one. In the page 16 of the slide.
Page 16. Let me go back to this page 16 here. Here. Page 16. Here.
Yes.
Okay.
In the main.
Yes.
In the main block.
In the main. Okay. Yeah.
Why we have to copy the device memory to host memory in the while loop? Yes, I would like to ask why we don't copy the memory.
Okay. This is copied because this is the DC. Okay, copy the DC to the host such that I can summing the remaining part of the sum of the. You see, DC contains the sum of all the different square of each block. Okay, right? You see here,
I see.
Okay, and then the rest I sum over all the partial sum of each block. Then I have to use the CPU to do it. Okay. Yeah.
Okay. I see.
Okay. Yeah. Okay.
Thank
Any
you.
other questions? Yeah.
Excuse me.
Yes.
I can. I enrolled this course on week 3, and I currently can access my TWCP1.
Oh, you just add the course. Last week.
I checked your directory. I wasn't in the list. Like my student number is not on it. I will provide my. This is my student. I provided the message here.
Can you send me an email? Tell me your student number so that.
I sent it on the Google Meet classroom here. The messaging section.
In the Google Meet.
Yeah.
What's your student number?
B11902 156.
Let me check whether I see it here. Okay. Let me see. B and then
11
11
90.
B11. Oh no, I don't see B11 and then
902.
Yeah, 02.
156.
1011. B11902 516.
156.